the opportunity to present our work on superconducting qubits and on magnons here. I would also like to apologize up front. So we don't have acoustic or mechanical systems in our circuits. But nevertheless, I hope you find this interesting. Okay, so the work I will present is mostly done in Karlsruhe at KIT. But we also do a bit of research, mostly on classical magnetism, classical spin waves, classical regime, at the local university, at Johannes Gutenberg University, Mainz. And yeah, the objective of our work is to realize this kind of circuit. So we have a superconducting qubit, probably a transmon qubit. We'll talk more about this a bit later. And then we couple it to a magnonic medium, so to a ferromagnet. And then we use this system to first excite a ferromagnet, to excite dynamic states in it, and also to probe the ferromagnet with this qubit, so with a quantum limit detector. This work is very similar to what Yasunube Nakamura presented earlier today. And in my talk, I will focus more on the superconducting qubit aspects of our research. And then in the final part, show first data on Magnon-polaritons, which we observed from room temperature down to millikelvin temperatures and low Magnon numbers. So now in the talk, first I will give you an introduction to the field, why this is interesting, why we are actually working on this. I will present you some of our results from the last year or so on superconducting circuits, and then talk about magnonics from the classical to the quantum regime. Yeah, most important, magnonics. So this deals with quantum, deals with information processing in magnetic materials. So to use spin waves to process information and to also implement logic elements. Here's a sketch of a spin wave, as you all know. And for example, with spin waves, one can realize a spin torque oscillator. This is a high frequency generator, if you like. It's based on two ferromagnetic layers separated by a spacer. And then if you send a DC current through this system, there's spin accumulation taking place in the upper electrode, and the magnetization starts to process, and microwave radiation is emitted. Or another implementation of information processing with magnons is depicted to the right. So there's a ferromagnetic film in a certain topology, and a spin wave is excited here, for example, by coupling an antenna to this ferromagnet, and then by, in addition, sending a DC current either from here to the left or to the right arm, the spin wave can be guided, so a logic element can be implemented here. Down here are typical limitations of these circuits. So the line width for the spin torque oscillator is larger than a megahertz, so it's not a particular small bandwidth oscillator. And for this device, the attenuation length of the spin wave is about 10 micrometer, so it's rather short. And this is due because we have strong Magnon damping, so the Magnon couples or scatters strongly with itself, so there are higher order Magnon scattering terms always involved if you have high Magnon number excitations. But also there's a strong coupling between the Magnon and phonon and Magnon and electrons. And all of this leads to strong Magnon damping. But to understand the physics of a single Magnon, one has to go to, well, to the quantum state, or at least to low levels of excitation, and research the spin waves. Then conventionally, Magnons are measured by two types of measurements, either by inelastic scattering with neutron, with photons, with electrons, or by ferromagnetic resonance techniques. In this conference, we heard already, we had a couple of talks talking about brilliant light scattering. That's a very straightforward method to measure and also create magnons by just inelastic scattering of light on a ferromagnet, and then either a magnet is created or it's absorbed. Or the same works for neutron or for electrons. The drawback of both of these classical measurements is that First, we have weak coupling of our measurement signal to the ferromagnet, and we require large flux. We have a small signal. Most measurements are taking place at 4 Kelvin or beyond, which means the ferromagnet is already thermally excited. So we've got lots of spin wave in the system, since KBT is much larger than the thermal, than the Magnon energy. And it's not so straightforward to access a Magnon ground state. One approach is to go to millikelvin temperatures and simply by freezing out all magnonic excitations in the circuit, and then also use ultra-low power spectroscopy and coherently couple the sensor to the ferromagnet. And this can be done by taking an artificial spin by a qubit, which we control precisely in amplitude and phase, and now extend our natural spin system, our ferromagnet, with this artificial spin, so that we have the qubit strongly coupled to the magnet, and then do controlled measurements on the ferromagnet to probe its state and its density of states, and then also determine the Magnon lifetime and the coherence directly. Now, a requirement for this implementation is to have strong coupling. The system is described by the James-Cummings Hamiltonian, which you also seen a couple of times during this conference. We have an harmonic oscillator, the Magnon, and a two-level system, a qubit, and then there's a coupling term. The strong coupling limit is reached if the coupling strength G, this term, is larger than the inverse lifetime of the Magnon and the qubit. And now if we plug in numbers for the qubit nowadays, for a superconducting qubit, we have lifetimes in excess of a microsecond, so a line width shorter than 1 megahertz. So the qubit looks actually good. For magnons, if you take a metallic ferromagnet, where the magnon scatters strongly with electrons at the Fermi level, then the magnon line width is on the order of 50 megahertz, which may be okay, but it's better to take a different ferromagnet, such as a magnetic insulator, yttrium iron garnet, YIG, and this has a line width of about 5 megahertz typically. And now, if we then calculate numerically the coupling rate depends on the number of spins we couple to and the mode volume. If you plug in numbers, we get a coupling strength of about 10 megahertz or larger. So it's possible to reach the strong coupling regime. And we also seen data actually earlier today by Yasunori Nakamura that it has been experimentally achieved. Now in the second part, after the introduction, I would like to talk about our work on superconducting qubits, in particular about multi-level spectroscopy on a new type of transmon qubit we investigated. It's called a concentric transmon, and it carries a magnetic dipole moment. And this may be of interest for spin physics, and also it has a high coherence. So the transmon, we had a short introduction today, but let me just sum it up. So a transmon is a very simple type of superconducting qubit. We have a Joseon junction here depicted by this cross, and this is a point-like nonlinear inductor, and it's capacity shunted. So it's an LC oscillator where the inductance is nonlinear. Therefore, we have an anharmonic potential and a certain number of discrete levels in that potential. It's anharmonic, so the energy difference between ground and first excited state differs from the transition from one to the second state. But we have more than two levels in that potential, usually. If you go into the rotating wave by considering the transition from ground to first excited state, this system can be approximated as a two-level system and then described by that spin operator, and we can then access all states on the Bloch surface. So we can create a coherent superposition of both states and also control the phase and achieve or target all the surface states. If you have such a system, just a Joseon junction capacitively shunted, then the transition frequencies are fixed, and experimentally this is sometimes not convenient. So it would be better to have some tunability in the circuit, and this is achieved by replacing one junction with two junctions. Then if a magnetic flux is applied, this is a DC squid, effectively it behaves as one Joseon junction where the Joseon inductance depends on the magnetic flux applied, and thereby the transition frequency changes as function of flux. So it means we can change magnetically the transition from ground to the first excited state, and also the higher transitions as well. So typically we operate the qubit with two Joseon junctions, so we have tunability of our transition frequencies. Now at KIT we started about 3-4 years ago to fabricate our own circuits. We have a clean room, we assembled deposition tools, so we can do conventional superconducting films like aluminum and niobium nitride. We also bought a commercial tool to give us or to provide aluminum oxide tunnel junctions using shadow abrasion technology. We brought up lithography and etching to form nano-sized circuits, as seen here. This is actually a Joseon tunnel junction. We have one electrode overlapping with the second electrode. In between there's a thin oxide layer, aluminum oxide, forming a Joseon tunnel barrier. There are a couple of dilution refrigerators in the lab. Here's a picture of one of them. It has about 40 centimeter of base plate, and we wired it up. So we have about 18 coaxial lines, more than 24 DC lines, a couple of microwave cryogenic amplifiers, filters, and some other microwave passive elements inside. Today we can cool down about 9 quantum chips simultaneously by using switches. So we can't measure them simultaneously, and we wouldn't have enough people or electronics, but we can put 9 qubits in and qubit chips in and cool it down and then keep it cold for an extended time and subsequently measure these chips. There's also measurement software, so we do spectroscopy and time domain measurements, and also we worked on software to simulate our quantum circuits, but also to control it. And I will talk about our software later shortly, so in case you're interested, we can also have a discussion after the talk. Okay, now I told you the transmon behaves as a 2-level system, but you can also do interesting experiments using the higher levels, so exploiting the weak anemonicity, because in effect it has at least 4 or 5 bound states. And this is interesting for, well, a couple of projects, for example, efficient and robust quantum gates, in particular C gates, phase gates, can be implemented by going to higher levels in the well. Or quantum cryptography can be improved, or can be actually implemented and can be improved, or quantum simulation. So if you have a 2-level system, this simulates or emulates a spin 1/2 particle. If we have 3 levels, then we can emulate a spin 1 particle. If we have more levels, then a spin 1/2 particle, and so on. So to implement a quantum simulator, having weak anemonicity is advantageous, and therefore we explored this a bit. That's a micrograph of the first transmon qubit we made. This is a qubit. These are 2 metallic plates on a silicon substrate, and then there's a Joseon junction, or actually 2 Joseon junctions shunting the metallic plates. So this is a circuit here depicted with 1 Joseon junction. It is capacitively coupled to an LC readout resonator. That's a lambda-half resonator, this meandered line here. And this readout resonator is capacitively coupled to a transmission line where we send the signals through. This is part of the transmission line. Now, the qubit is read out dispersively, which means depending on its quantum state, it affects the effective impedance of the readout resonator, and therefore the readout resonator's frequency is shifted slightly, and we measure this shift. Both resonator and qubits are detuned in frequency. typically about a gigahertz or more. Yeah, this was a very simple implementation. We had like 60-year technology for the Josephson junctions, just two metallic overlapping stripes. But they put us into the transmon regime, and we did mostly spectroscopic measurements with multiple tones. The first thing you do is high-power spectroscopy. So you have your qubit, and then you start to sweep your excitation frequency and power. At low power and high frequencies, we then observe a transition. If you increase power, this broadens. There's power broadening, homogeneous broadening happening. If you go to higher power and lower frequencies, a second transition appears, and at even higher power and lower frequencies, another one, and even, I think here's even a small transition happening. We did simulations of our circuit and some more measurements, and then could label these transitions. So here, this is first transition from ground to first excited state, so from here to here. This one is a 2-photon transition from ground to the second state. This one a 3-photon transition, and this one a 4-photon transition, depicted here in blue, from here to there. And here's a sketch of the potential of this anharmonic system. So we have multi-photon transitions, and this can be these values can be used to determine the qubit parameters, so to check, make a systematic check on the experiment. A next experiment is then to dynamically couple these levels. For example, couple the ground state with the second level by applying a strong drive. So that's the drive depicted by red. And then in the rotating wave, there's a new energy diagram. There are also AC, there's also Rabi splittings. So in the rotating wave, these degenerated levels, they split. And with another tone, or with two more tones, actually, the new energy diagram can be measured. That's seen here. So we apply a probe tone. There's one tone to couple ground to the second state. Then there's another tone to probe it, and another one to drive. And then we get this data. We did also simulations, and we see this avoid level crossings, or they're called Outlier-Towns doublets, and they correspond to transition between 3' and 0', or 3' to 2'. That's this transition, or 2', 0' to 1', or 2' to 1'. That's that transition. Okay, so this was our first experiments on transmon qubits. I haven't shown any lifetime or any coherence data. We did some measurements there, but coherence was rather short for a couple of reasons. One, we had such a structure. So this is a parallel plate. It had a parallel plate structure on a substrate, and it can radiate. Once it's excited, it radiates into free space. So you've got lots of radiation loss, limiting your lifetime. This geometry can be improved. So one can wrap, say, the left electrode around the right one. So you get a horseshoe geometry, or in extreme case, it's a concentric or a coaxial geometry, where we have one electrode capacitively coupled to the ring, the disk capacitively coupled to the outer ring electrode, and then there's one or maybe two Josephson junctions providing the inductive shunt between them. So in the far field, this object has no radiation field, which means there's no radiative loss in the far field. However, if you're in the near field, so if you bring another of these transmon, this circuit, close to it, they still couple each other, so they still see electric fields. So it's still possible to couple to that circuit, but you have to get close to it with your readout resonator, coupling bus, or another concentric transmon. That's a micrograph of this circuit. We have not one junction, but two junctions, making it a gradometric structure. And there's a part of the readout resonator capacitively coupled to the system. The level detuning is done by applying a local flux to the circuit, and due to the geometry we have a larger mutual inductance to the right half loop than to the left half loop. Therefore effectively we can change the effective flux in this DC squid and change the effective critical current and the qubit splittings. Here's a lumped element diagram. So the black dot corresponds to the center electrode. We have the two Josephson junctions, top and bottom. Then the concentric loop is it's simplified, but it's depicted here as just a serial connection of 4 geometric inductances, and there's a capacitive shunt to the center, to the left and right. And to the right we have a flux bias or a current source with an inductor applying flux bias to the system. A readout again is done dispersively, so the readout resonator is detuned in frequency from the qubit. It's also a very simple design. It's a microstrip, so we have a metallization underneath the substrate. Then the flux bias line is implemented in a CPW, so in a coplanar geometry, to keep the electric and magnetic fields localized, so to not couple too strongly to the qubit. And also the gap between both electrodes is large, it's about 35 micron, and therefore we couple weakly to dielectric loss states at the surface of our electrodes. So to two-level systems, TLSs, which can be on or close to resonance of our qubit, and if you couple to them they can absorb energy and simply reduce the qubit lifetime. So it's just a trick to increase lifetime without dealing too much with material surface or material properties of our metallic film. Yeah, we used a combination of optical and E-beam lithography, E-beam lithography for the tunnel junction, for the readout resonator and the flux bias. We did optically. Please.
So what is the advantage of having a microstrip
design,
having ground plane?
Yeah. So we are also pulling, actually, thanks for the question, didn't mention it. So we are pulling the electric fields into the substrate. If you have just this system without a ground plane, then the electric fields are strongest on the surface. So they would couple to lots of TLSs. If you have a metallic ground plane, then a larger fraction goes into the substrate, and the substrate is of high quality. So we reduce coupling to surface TLSs. I should, yeah, it's just a trick to reduce, coupling to dielectric, to reduce the dielectric loss of the system. Here's a sketch of the pulsed time domain measurements. It's a complicated setup, but I would like to explain it briefly. So we have two tones, one for the qubit and one for the readout resonator. Both are modulated in real and imaginary part or amplitude phase. So we do pulse shaping on both signals, both tones. They are created here and here. They are amplified, actually attenuated a bit here again. They are combined, and then in a single coaxial line, we send these two tones down into the cryostat, down to it's further attenuated, thermalized. The signals go to the sample via the circulator. The qubit manipulation tone drives the qubit directly, and the readout tone just excites the resonator. And after passing the resonator, it gets back to the transmission line and gets filtered, amplified at 4 Kelvin, gets to room temperature, gets further amplified, and then it's mixed down. So we have a few gigahertz signal here. Also here we have down conversion into the megahertz regime, and then we digitize it with an analog to digital converter here.
We have two circulators at 20 million. Please? What is the second circulator for?
Oh, there's a second, yeah. So we want to, this is a hot device. It's an active microwave amplifier.
How do we couple it?
Yeah, one to decouple, right. So each of them gives us about 20 dB isolation, but we want to have more, like 40 dB or even, yeah. So it's simply decoupling. Here are typical sequences. So we do, well, the first measurement you probably do is just a Rabi measurement, which means you apply a microwave drive to the qubit for a certain time, delta t, and then read out the qubit. Readout means we apply a tone to the readout resonator and digitize it. Lifetime measurement, that's just a pi pulse waiting for delta t, so it relaxes back to the ground. Doing the readout, there's a Ramsey measurement, which is a pi over 2, a wait time pi over 2, or an Hahn echo measurement, that's pi over 2, a wait time of delta t half, refocusing pi pulse, and another wait time of delta t over 2, followed by pi over 2 and a readout pulse. So these are the typical sequences. That's the lifetime measurement. So just a pi pulse waiting readout, and we get about 9.1 microseconds for that particular sample. We can also do numerics, and we can calculate the loss, expected loss for this circuit by considering the Purcell loss, so the loss induced by coupling to the readout resonator and to the flux bias line, by coupling to dielectric defects, and also the radiative loss. All these losses contribute, and if we sum it up, we get about 9 microseconds, so it matches well our measured value. For T2, this is actually the spin echo T2, we also get about 10 microseconds. This should be, in theory, T1 limited. It means we still have some dephasing in the system, and we can't really cancel out by the refocusing pulse. The pure T2 measurement, the Ramsey T2, is about 2.2 microseconds. But that's still a good value, so it's beyond a microsecond of T2 star. And I guess in particular because we have rather large areas for flux biasing in this concentric transmon. So there's a bit of dephasing expected just because we have these large loop areas. Now, okay, yeah?
Compared to quantum qubit, for example, by IBM groups,
Yeah.
it's same order or smaller.
It's a bit smaller than.
But they have the T2 star tens of microseconds.
Yeah, the 2D versions. Yeah, I think so. But I think that, well, they're also using complicated materials sometimes, like or more challenging, like titanium nitride or niobium nitride, maybe fractional niobium. So this is all done with aluminum technology and with liftoff, which is there are ways to actually improve the material qualities here. So we also did a pulsed measurement where we changed the qubit frequency by applying a fast flux bias to the qubit. That's the measurement sequence. We start in ground state, do a pi over 2, then change the level splitting by the qubit magnetically. This corresponds to a controlled precession in the equatorial plane of our qubit. We do this for a time delta t, followed by, well, first bringing back to the level before, another pi over 2 pulse, and readout. And then in measurement we get an oscillation between 1 and -1, and so there's a controlled precession with the precession frequency depending on the detuning. So depending on the detuning parts, or the height of this tuning. So this can be set to a large range, up to I think up to 1 over 100, 150 megahertz, so close to the unimonicity. Now what we then have is well, our controlled precessions around all axes of the glossphere, around the x, y, and z axis. And this can be quantized by benchmarking. It's a complicated system, but what you see here are just the combinations of various types of pulses. So a pulse around the x-axis, followed around the pulse around the z, or the y-axis, or back, and with different lengths and signs. The expected values are depicted in gray, the measured one in blue, and by using several microwave techniques like single sideband mixing and shaped pulses by dynamic removal by adiabatic gating to reduce the population of the second level and beyond, we get then a gauge fidelity. We do benchmarking of 99.54%. It's just a number. Maybe this is more interesting. So we can do a combination of pulses. First, starting ground state, do a rotation around the y-axis, followed by rotation around the z-axis. So here, around z-axis, and then around x-axis, back to ground state. So we have this trajectory on the blocks here. Now, the concentric transmon is a great qubit, has good lifetimes, we can control it well, but there's a catch. And we have some geometric inductance in this circuit. Here's another lumped element description of the system. So we have these both loops to the left and right. This can be simplified by combining it into such a circuit where we have a geometric inductive shunt to one side. It can be even simplified by going to this circuit description with the Josephson junction being in series connection to an inductance being capacitively shunted. And now to determine all these values, I, C, L, and C, we did spectroscopy over large ranges and also high-power spectroscopy, did lots of fittings, and then came up with a value for this geometric effective shunt inductance. It's about 0.6 nanohenry. This means we also did further studies using black box quantization and some further, more sophisticated methods. It means, so we have a geometric inductance in this circuit, and it also, so the consequence is the system can carry a persistent current. So it has a magnetic dipole, not at the sweet spot, so not here, but if we are off the sweet spot, there's effective, persistent current, effective magnetic dipole in the system, and this can be used to create non-trivial couplings between artificial spin systems. This is one qubit. So its magnetic dipole polarizes this qubit along the horizontal axis. It means we have sigma X coupling, that's always present, but also sigma C coupling, magnetic coupling, and CC coupling along the horizontal line or around the vertical line. Due to the gravimetric layout, we have only sigma X coupling. Now, this is interesting to create, to study spin arrays with non-trivial couplings. For example, a quantum simulator can be realized with such a bilinear array. We did some theoretical studies on this. So the one-dimensional Fermi-Hubbard system can be emulated with such a chain of concentric transmons. Okay, this is the last slide on the qubit, superconducting qubit. We can also do controlled swap experiments. So that's a scheme. So we excite the qubit, we detune it, bring it on resonance for a certain time with another quantum system, a resonator or another qubit, or maybe a magnon, then detune it back and read it out. So we did not test qubit to magnon coupling, but qubit to electromagnetic resonator. And that's the data. This corresponds to the detuning. Here we have maximum swaps. That's the line cut to the right along this axis. And it means there's a controlled coherent oscillation between our excited qubit and the first not excited resonator. So this technology of implementing quantum swaps is set up. It's working. Also the components required, they're all tested and implemented. Now the next step for us is to do a controlled quantum swap between the qubit and the ferromagnetic system. So a magnon or magnonic system. This brings me to the last part of my talk. YIG, that's our ferromagnetic system of choice. Yasunori Nakamura already presented its properties today. It's kind of the fruit fly of magnetism. It has extremely good magnetic properties. In particular, the spin wave damping is weak. So it has a damping coefficient of 10 to minus 5, 10 to minus 4. Also, spin wave decay length is on the order of centimeters, while it's also room temperature magnet. In particular, it's a ferrimagnet, but it can be approximated as a ferromagnet. It has a high spin density and it's a bit anisotropic, so there's a soft magnetic or weak magnetic and hard magnetic axis. The soft magnetic axis is the 110 axis. Magnons were also introduced today. Just want to show you the Hamiltonian. So we have the Zeeman term and the direct exchange interaction term by the spins. That's a typical description or pictorial the description of a spin wave. This can be a standing or traveling spin wave depending on the k vector, k0 or k larger than 0. And the magnetization, precessing magnetization in the ferromagnet is described by the Landau-Lifshitz equation seen here. If it's a standing precession, a standing wave, then the system can be described as a macro spin just by the combination of all spins precessing in phase with the same frequency, and in that case the precessing frequency is the Guettel frequency is given by this equation, so it's linear proportional to the applied outer magnetic field. Okay, so for small excitations, so for single magnons, few magnons, then the effective magnetization can be, it's split into a static part and dynamic part. The static part that's reduced with the opening angle of the magnetization can be approximated as this. So it scales quadratically with the opening angle, and the dynamic magnetization scales linearly with the opening angle. And usually for single magnons, we are obviously close to the c-axis, so having small angles. The field of quantum magnonics, or magnonics with cavities, Magnon-polaritons, that's a dynamically growing field. So the very first publication on Magnon cavity experiments was Tabuchi et al. From Nakamura's group in 2014, in May 2014. Then, like 2 weeks later, there was a publication from the Yale group. There were more papers this year, experimental work on high cooperativity between magnons at microwave frequencies, some theoretical work. This is another work where they observed coupling at room temperature and millikelvin of various modes, Guettel mode and some higher order modes. The work we also learned about today by Nakamura on coupling between a superconducting qubit and a ferromagnet, and even some ultra-high cooperativity experiments. And that's an incomplete list, so there's lots more actually happening since in the last 2 years. This is our contribution. So we also are working with 3D cavities. That's an image of an aluminum cavity, but we also have copper cavity, which can be placed in a magnetic field at millikelvin temperatures. We use this to couple our cavity or resonator to the ferromagnet. Here are some electromagnetic or magnetic field simulations. That's the coupling to the cavity. The Higgs sphere would be placed or is placed at the position of highest magnetic field antinode. There are more modes in the system. That's the ground mode. Second mode has also a large magnetic field, rather large magnetic field here. Third mode and so on also exists. So one can couple to several modes of the cavity. We are, on this project, we're actually working in 2 different laboratories. So there's one in Mainz. This is part of the chair of Matthias Kloy. And there we installed or set up a measurement setup to work between 4 Kelvin up to room temperature using rather high magnetic fields up to a few Tesla. we did first studies on YIG spheres, commercially obtained, but we would like to extend it to thin film, thin magnetic films. That's the first data we obtained in Mainz by coupling this cavity to a YIG sphere. In Karlsruhe, we did similar efforts, and so we also assembled a measurement setup with a homemade magnetic coil, some iron yoke, and okay, this is now placed at room temperature, but we plan to put it at millikelvin and then study well, few to single Magnon excitations and also do line width and noise measurements there. Also extended by coupling to a superconducting qubit. That's the first data from Mainz. So starting at room temperature, cooling down to about 5 Kelvin. We use this kind of cavity. It's a double reentrant cavity, giving stronger magnetic fields with a bright mode. But it's just a way to enhance the coupling strength. So we then measured the coupling strength as function of temperature, also the remanence field of the voidal level crossing here. This also changes as function of temperature due to an increase of internal magnetization of our sphere. If you now measure at several temperatures, there are some inhomogeneous modes appearing and disappearing. And this is something we don't fully understand now. We're investigating this closer. It was also observed by Zhang, but they only measured at room temperature millikelvin. So we see something happening at about 150 millikelvin and then disappearing below 100 Kelvin. That's data we've taken a couple of days or weeks ago, so it's still under evaluation.
So when you say disappear, does it just line width would get very low and then you cannot see it anymore?
I think the line width doesn't, we're still looking into the data actually, but, so I think the line width of the cavity doesn't change much. Maybe we did test measurements, so it's cavity changes slightly, but also in frequency, but this probably doesn't really explain it. YIG is a complicated system, and there are several phase transitions. Maybe that's an indicator here. That's our data, our lowest data taken so far. In Karlsruhe, at 500 millikelvin in a solenoid system, there's again there's a void level crossing on resonance. We have a Magnon line width at these temperatures at about 2.4 megahertz. There is a coupling strength of about 25 to 30 megahertz, and also we observe non-uniform modes in this circuit. Now, as an outlook, so far we did coupled two harmonic systems classically, but the objective is to have a qubit coupled to the ferromagnet. Straightforward implementation is seen here, so there's a direct magnetic coupling, but that's a challenge because we need to apply a magnetic field to the ferromagnet, but we don't want to decohere the qubit, so it's better to use a coupling element like a bus resonator or some other means to physically separate the qubit from the ferromagnet and have low magnetic field or maybe zero magnetic field at the qubit. Also, we would need a separate readout resonator for the qubit, and this could come in from the other side. So very nice implementation was presented by Nakamura. That's this 3D cavity having different modes, first, second, third mode, to couple to YIG, also to couple YIG to the qubit and qubit to the feed line, or qubit to the readout resonator to the feed line. That's a good implementation, certainly. So 3D transmons we also have in our laboratory. We made it for a different project, but it's available. So that's a sketch, a micrograph of the circuit. Here's one junction, just part of the cavity. We did time domain and Ramsey and T2 measurements, T2 star measurements. That's the Ramsey data we've taken. So on the first sample, we had about 50 microsecond coherence, and T2 star about 30 microseconds. So it's a well-behaved 3D transmon chip. Now, I was presenting various aspects of our research. It's just a graphical summary of what we did. And we would like to combine, so we'd like to have the qubit coupled to the Magnon. The challenge is we have no Christ died yet. So it got ordered, got delayed. We hope in July we'll have it. So in the meantime, we've been working on all these other pieces. And I showed you some of the results. Some project which we put some effort in is software. So we're using Python as particularly IPython notebooks for our measurement and simulation scripts. This is a modern based data format to store 1, 2, 3-dimensional data. There's a 1 and 2-dimensional data viewer. There's already a large library of instruments. It's all open source, obviously. And in particular, we've been working on data fitting of resonators. So we implemented the circle fitting algorithm. Don't want to go into detail, but it's kind of a robust approach. If you have a vector network analyzer, so if you take complex scattering data, you may want to implement the circle fit algorithm. We published it last year, and it's implemented in this software. So yeah, being open source, would like to share, and if you're interested, we can have a discussion later on. Would like that. Let me conclude by thanking our team in Karlsruhe and Mainz. Here's a summary of the results I presented. And let me thank you, all of you, for your attention. Thanks. Yeah.
Okay, thank you very much. Maybe there are some more tricky questions. Yes?
So yes, for the data with the coupling of the Higgs sphere in the cavity, right? So you showed that the resonance field changes with temperature. So why should it change if the saturation magnetization changes? Because I thought if it's a sphere, that should not matter, unless it's not a fundamental mode you're looking at.
It is I think it's a fundamental. That's a Kittel mode we're looking at. But I think the system, yeah, again, this is fresh data. We still need to analyze it. I could speculate. I think it's not fully saturated magnetically here.
Okay, because for a sphere, the Kittel mode is independent of the saturation magnetization.
But not if it's not fully saturated. Yes. So if you're measuring, say, off-axis, and then there's some tilting in the effective magnetization, this is probably what's happening. I think the frequency is maybe 6 gigahertz, or so it's not. Yeah.
So you showed your numbers for coherence for the 3D transmon, and the T2 star was T1 limited, but the T2 the echo time seemed to be shorter.
For the 3D transmon, or okay? Oh, sorry, I was wrong way. So the T2 is okay, this one. So the T2 star is T1 limited.
Yeah.
The T2, Ramsey T2, not.
So the T2 star is not the Ramsey T2 in your case?
No, we use different, yeah. Yeah, so there's a bit of confusion in the fields. So this is maybe not generally accepted. This is Ramsey, and this is echo. Yeah, thanks. Yeah.
So between your research cubes, you had both electrostatic and inductive coupling. So what's the strength of the cube?
It depends on geometry, but it's it was way too much. 10 to 30 megahertz. We're doing simulations on it, so it's not like a strong, this one, it's not like strongly inductively coupled or CC coupled, but they're on the same scale. So this, I mean, it really depends how close you bring it together. So like the same size, yeah, say 10, 15, 20 megahertz, both.
So in this geometry, we were several transmons next to another one, next to each other. Do you still plan to use flux lines? Because it seems not so obvious where to place the flux lines.
That's a good point. So we haven't thought so much in depth about that. How to flux splice it? Yeah. Yeah.
And also, what's the quality factor of your straight line?
The what?
What's the total factor of your resonator?
Of the readout resonator? Well, it's overcoupled to the feed line, so it's about 2,000 to 5,000. But that's a readout resonator. But yeah. So for the flux bias, well, I mean, it has to be, gradometrically coupled as well. So I guess I would cup in off-center from here, and then there's going to be crosstalk, which I have to calibrate out.
But if you have 9 qubits, then
Well, I need 9 current or maybe 8 current sources. Yeah. So I need several. Sure. I mean, for each qubit, I would need 1 current source. Yeah. Or 1 flux bias line.
The same question.
Same question, great.
Okay.
So how many qubits will you have in your new fridge?
Maybe just 1. Yeah. No. So it's a larger group, and there are lots of students, lots of projects going on, and cooling down takes so much time. We decided to simply use that volume and wire it up, not as much as we could, but so to keep cold for an extended time. Yeah.
Any more questions? Seems to be the case. So let's
Okay.
thank both speakers of the session again.
Okay.